Here is another mass current technique. Let's call this MC2. We saw MC.1 last time. So we're going to start calling this MC2. MC, mass current, that is, number 2. So this time again, we have masses. Um, let's say this is one of them. Here we go. Notice the diamond. That makes the circuit interesting, but also slightly difficult. Slightly, not too much. So this time we are gonna have 4 meshes. Okay, with various elements, every with plus. So this is 6 ohm on the top, 4 ohm on the other side, and this is plus minus P sub S, 2 Henry. This diamond has 2 P naught, but notice this current source, 0.25 farad. I have a squeezing pipe here, 0.25 farad. 2 ohm resistor, ground symbol. So this is the current source IS. We're almost done here. The P naught we've been talking here is the voltage across the 2 ohm resistor, P naught. So what is the goal? The goal is to come up with a matrix to express the KVL equivalence. Let's go ahead naming the meshes. Mesh number 1, soak the number 1 window. Mesh number 2, soak the second window, as we often say. Number 3, I sub 3 here, and I sub 4 here. Sorry about the messy handwriting. So let's go ahead. Remember that the voltage across the inductor is given by L di dt, and using the operator notation capital D, which is d dt, we have I sub L here. P sub L is L di L. Now, if we have the current passing through the capacitor, we will have I sub C dV dt, d, the voltage across the capacitor. So we can recover the voltage across the capacitor by doing an inverse operation of differentiation, namely integration. So we can express this as 1 over C d minus 1, which is inverse of differentiation I sub C. This is 1 over C here. So if we look at the two meshes I1 and I2, we realize there's a competition across the diamond branch, and it looks like the diamond is pointing upward in favor of I sub 2. So I sub 2 minus I sub 1, which is the resultant current on that branch, is equal to 2 V naught. The diamond has a current source which is dependent on the voltage V naught. So notice that. And what is V naught? V naught is the voltage across the 2 ohm resistor. And noticing the plus and minus the way we have, we end up finding V naught equals 2 times the current balance. And to make the plus on the top, we ought to have I3 prevailing over I sub 4. So 2 I3 minus I4. is V naught. Okay, so we can plug this lower expression for V naught on the upper one. So that will give us I2 minus I1 and minus 4I3, then plus 4I4 equals 0. And since we are wanting to have the matrix expression, let's rearrange this in this form. And while I add it, let me draw this box to keep this expression in. So we have minus 1 times I sub 1. Notice I sub 1 has a sign minus, plus 1 times I sub 2, plus minus 4 times I sub 3, plus 4 times I sub 4 equals 0. Next, let's consider the supermesh 1 and 2. Supermesh 1 and 2. Why supermesh? The reason is we are wanting to use mesh current technique. So as you go through the meshes, we go around a closed path and collect the voltages on the path. While we do so, on either mesh 1 or mesh 2, we would have to go through the branch that has got the current source, namely 2V naught. So there's no way to tell how much voltage is across this source yet. So we like to avoid it, and the way to do that is go down the big loop containing mesh number 1, mesh number 2. So that is the reason that we're taking super mesh. So as we go through the path, we will need to remember the way to get the voltage across the inductor and also across the capacitor. So remembering piece of L, where L is 2 Henry, is given by LD, the net current. So we're going to start at that point. So that will give us 2D net current I1 minus I3, because we are in mesh number 1 at this point, and whichever mesh we are in, the current in that mesh prevails. Going with the house rule, plus 6 I sub 1, that is the voltage across the 6 ohm resistor. We will continue to go through mesh number 2 at this point, so plus 4I2 and then plus V sub S. Now we have the voltage across the capacitor, and that expression has 1 over C, which is 1 over 0.25, so that will be 4, of course, and then D minus 1 and I balance. We're in mesh number 2, so current in mesh 2 prevails over current in mesh 4. I2 minus I4 equals 0. If we expand this expression, we will get 2D I sub 1 minus 2D I sub 3 plus 6I1 plus 4I2 plus V sub S plus 4D minus 1 I sub 2 minus 4D minus 1 I sub 4 equals 0. Once again, we can group this conveniently the way we want it to express in the matrix. So we're going to get 6 plus 2D1. We're collecting the terms with I sub 1. So this got I sub 1 plus 4 plus 4d minus 1 I sub 2 plus minus 2d I sub 3 plus minus 4d minus 1 I sub 4 equals minus ps. Next, in next number 3, we realize I sub 3 is the same as I sub s, which is also called as KCL. So let's express this also in a box rather nicely. So nothing times I1 plus nothing times I2 plus 1 times I3 plus nothing times I4 equals IS. Now, what we see is in mesh number 4, we have I should have it in this thing here. Okay, so that will make it better. 2 times I4 minus I3. We are in mesh number 4, remember that? And the house rule dictates whichever mesh we are in, the current in that mesh prevails over everything. Plus the voltage across the 0.25 farad capacitor is 1 over 0.25. Shall I say that's a 4? Okay. And D minus 1, the balance current, which is I4 minus I2, again applying the house rule, equals 0. Now, we can simplify this. So that's going to give you 2 I4 minus 2 I3 plus 4 D minus 1 I sub 4 minus 4 D minus 1 I sub 2 equals 0. So one more time we have the box. So we would have all the 4 equations to put in the matrix. So this is 0 times I1 plus minus 4D minus 1 I2 plus minus 2 I3. Need to be careful here. I3 plus 2 plus 4D minus 1 times I4 equals 0. So therefore, finally, the matrix equation is okay, minus 1, 1, minus 4, 4. I sub 1, I sub 2, I sub 3, I sub 4. This is getting compact here. These are tricky things. So it's 0. The next one has 6 plus 2d. 6 plus 2d, 4 plus 4d minus 1 minus 2d minus 4d minus 1 minus ps. Then 0, 0, 1, 0 is is. Then 0 minus 4d minus 1 minus 2, 2 plus 4d minus 1 becomes 0. There you go. So this is the matrix equation. In essence, we call it sometimes the admittance matrix times the current vector is the voltage vector. This is another form of Ohm's law, where Y is the admittance. That's what it's called, Ohm's law, basically. Well, this is how we work when we have the eyeball on the matrix. Hope you enjoyed it. Take care.